So we are going to talk about falling objects today. Galileo was kind of the first to come up with this hypothesis that all objects fall with the same constant acceleration. And everybody's like, but what about, a bowling ball and a feather? If you drop both of those at the same time, they're obviously not going to fall at the same rate. The only problem is if you drop a feather in our atmosphere, there's all this air. It feels like it's empty space, but it's actually not. So if you were to drop a bowling ball and a feather in completely empty space, we call it evacuated space or a vacuum, they drop at the same rate. But the problem is when we're dropping stuff on Earth in our atmosphere, you drop a feather, the way it's spread out, then it's really prone to air resistance. So another example I give is drop a pen and a textbook at the same time. The pen is much, much, much lighter, but it drops at the same rate as a textbook. Both of them are a little bit more aerodynamic and not as prone to air resistance. And so therefore, something like a pen and a textbook will drop at the same rate. So there is this constant acceleration at which objects fall. Well, specifically when they're on Earth. Okay? So this is what it kind of looks like. If a ball is thrown up and then returns to Earth, this is what it looks like. So we want to consider a few different situations here, a few different places in its motion. So we're going to talk about the moment it leaves this guy's hand. It's going up with a certain velocity. Okay? And then at some point, over half the way to its top, to its highest point, it's going to be half of the velocity. And then at its highest point, for this split second, it reaches a velocity of 0. Anything that's changing direction has to reach a velocity of 0 at some point. Okay? So of course, we're only talking about this happens for a split second, a fraction of a second, right? It's at 20 at a fraction of a second. It's at 10 meters per second for a fraction of a second. It's at 0 meters per second for a fraction of a second. Another thing that we can count on then is that when it reached this same height on the way down, then it's going negative 10 meters per second. So at the same height, they have the same velocity. It's just in opposite directions, right? One's going up, one's going down. And so that we can count on the same thing down here. If it left the guy's hand at 20 meters per second, then it'll probably come back down at 20 meters per second at that point. Okay, so those are things we know about this kind of motion, okay, when something is thrown up and then comes down. So, again, let's just look at those points a little bit closer, okay? So, if we know that V and A are in opposite directions, which they are at point A, right? Because we know the velocity is upwards and the acceleration is down, because that's what acceleration does on Earth. Acceleration due to gravity is always pushing us down towards the Earth. So the velocity is upwards because you threw it upwards, but the acceleration is downwards, which is exactly why it slows down until it gets to its highest point. So we know the object's slowing down. And then we know if they're in the same direction, so when the ball starts going down, the velocity is down and the acceleration is down, then the object is speeding up. And so that's when things are falling towards Earth, they're speeding up. If we try to throw them against the Earth's gravity, then they will slow down as they go up, unless you have enough force to overcome that force of gravity. Okay, so at point A, our distance, we have gone 0 meters, okay? Actually, I should say displacement. We're going to be talking about displacement and not distance. The velocity is at its positive maximum. So we're going to think of up as positive and down as negative. You can see I defined my direction right over there. Up is positive. So it's at its positive maximum, and acceleration due to gravity is always going to be constant. It's always going to be negative 9.81 meters per second squared. Okay? So this is your acceleration due to gravity. So that's the thing that's going to be constant throughout this whole thing. Okay? So that's what's happening at point A. okay, is that we have no displacement yet, but we're at our positive maximum. So remember, we're thinking at the moment, at the fraction of a second that the ball is released from the hand. Okay, so let's look at the motion from A to B. So the displacement is increasing, right? Because it's getting further and further away from its starting point. Okay, so this is obviously when there's, or at the top is when it's at its maximum displacement. So this velocity is positive because it's still going up, but it is decreasing, right? Because it's getting slower and slower as it gets to point B. But our acceleration is always constant. If you're throwing something, if something's due to Earth's gravity, acceleration has to be constant. It's always at negative 9.81 meters per second. Now, at B, this is when you have maximum displacement, okay? Because it's furthest away from its starting point, because as soon as it starts falling down, it's getting closer to its starting point again, okay? What's my velocity at point B? That is when it reaches zero for that small fraction of a second, okay? For something to change directions, it has to reach a velocity of zero in between, even if you can't tell exactly when that velocity is zero. It is going to reach zero for a fraction of a second, but of course, my acceleration, it's all due to gravity, right? So it's going to be negative 9.81 meters per second squared. Let's look at from point B to point C, what's happening in there. So my displacement is positive, but it's decreasing because now it's going back down towards its starting point. The velocity is negative now because guess what? It's going down. Okay, that's all that means. Remember, since up is positive, then if it's going down, it's negative, okay? Why is D still positive here? It's still above, it's still upwards from its starting point. So speed is increasing, but in the negative direction now because it's going down. And our acceleration, guess what? Surprise, surprise, is still exactly the same. Now at C, this is where displacement goes back to 0 meters because here's where it started, here's where it ended. So displacement, we're only looking in the y direction here. So displacement is 0 at that point. The velocity is at its negative maximum. Okay, what does that mean? Remember, here it's at its positive max. Okay, at this point, the velocity. So here, velocity is at its negative maximum. Right, so if it was 20 meters per second at point A, then at point C, it should be at negative 20 meters per second. Okay? And surprise, surprise, the acceleration is still negative 9.81 meters per second squared. Can you believe it? Okay, and so that's how falling objects works. So you just really need to know what's going on at those 3 points and what's happening in between those 3 points as well. That's really, really important because then we can use all our acceleration equations that we learned in the last lesson and apply them to falling objects. But now, when it's a falling objects question, we have all this information, we have all this stuff that's implied, but not explicitly told to us in the example, okay? So let's go over a couple of those examples. So we have a foul ball being hit straight up in the air with a speed of 25 meters per second, okay? So we want to know how high does it go and how long is it in the air? Okay, so really, really important. So what's going on? We have it being hit up, right? Going like this and then coming back down and doing that, okay? So it's straight up in the air and then coming back down. So the initial speed here is, guess what? 25 meters per second, okay? So like I said, try to start with listing what you have. 25 meters per second. That's my initial velocity. What else do I know? So it looks like you got no information whatsoever. But if we're dealing with a falling objects question, we do know something else. We know the acceleration, right? Because it was never changing. It's negative 9.81 meters per second squared. Okay, so just for point or for part A, I want to know how high does it go. So here's the displacement. Okay, so I want to know the maximum height. So there is something else we know about this point. Something very, very special. What do we know about the velocity up at this point? It's 0. So that's the really helpful thing about the highest point, is we know that the velocity is 0. So a lot of these questions look like you have no information, and surprise, surprise, you actually have way more than you thought. So we know it's 0 meters per second at the top, okay? So this is only for question A. For question B, we won't use this, okay? So we're looking for our displacement. So again, you look at your acceleration equations on your data sheet and you look for which one fits this scenario. I need something that's not working with time because I don't have time, and that's actually what I need to find in part B. So if you look, there's actually only one equation in which we don't have time, and it's this one. Okay? And look at that, we know final velocity, we know initial velocity, we know acceleration, and we're looking for displacement. Isn't that nice? One other thing I need you to do, though, before you do any calculations, define your positive direction. Okay, so here we're going to define upwards as positive. What's another thing we know about final velocity? We know it's 0. So here I'm going to cross that out and say, oh yeah, that's 0. 0 squared is still 0. Okay, it makes rearranging just a little bit easier. So if I want to get the displacement, I'd have to subtract vi squared from both sides and divide by 2a. So that's what I get. I get negative vi squared divided by 2 times a. Okay. And then I'm going to calculate that. So negative 25 meters per second squared. I left the negative outside the brackets because it's saying vi squared needs to be negative no matter what. And then I can divide that by 2 times the acceleration, which is negative 9.81 meters per second squared. Really important that you have your negatives in the correct place. So remember, acceleration is downwards, and we define upwards as positive. Okay? All right, so what do we get for our displacement? In the end, we should get 32 meters. Also, take a look. I was only given one value in the question, and it was 2 significant digits. So and here we're dividing, so my answer should also be 2 significant digits. Okay, so there's my displacement. And now for part B, I need to find my acceleration. Okay? So there's a few ways that we could do this. We could find acceleration based on the highest height. We could use that displacement if we wanted to, okay? But there's another way we can do this because we still know our acceleration. So now I'm going to ignore the whole highest height thing, okay? And I'm going to look at maybe this, because do you know what the final velocity will be at this point? Well, my initial velocity was 25. So my final velocity, if it's going down to the same height, should be negative 25. Okay, so that's another way. So a lot of people will find the time to this highest height here and then multiply it by 2. You can absolutely do that. I'm just giving you maybe an even easier way to do this because a lot of people forget, oh, I also have that. Okay, so that's just another way to do that. And then in that case, I can use this equation, which is a nice easy one to rearrange for time. Okay, because if I do, it just looks something like this. These are all vectors. I just start getting lazy and stop drawing them. When we're dealing with these kind of questions, we know we're always dealing with vectors now. Okay, so time should equal to negative 25 meters per second minus 25 meters per second. Okay. And then I'm going to divide that by my acceleration, which is negative 9.81 meters per second. So again, it's so important that you have the correct signs in here. If you just did 25 minus 25, you might think that that's 0 and then it's in the air for 0 minutes. Absolutely not the case, right? Negative 25 minus 25 is negative 50. So it makes a big difference. So be careful with those signs. And we get a time of 5.1 seconds when I work that out. Oopsie. Okay, So there we go. So that's how we can use our acceleration equations in a falling objects situation. Just remember, there's so much background information because you know it's a falling objects question that it's not going to be explicitly given to you in the question. So you just need to know about this kind of situation. Moving on to our next example here, we have a helicopter ascending vertically with a speed of 7.5 meters per second. So that one, again, it's really tricky. Physics is just as much about reading comprehension as it is about physics, because think about it, it's all word problems. So if it's ascending vertically at a speed of 7.5 meters per second, it just gave you actually the thing's initial velocity, if you can believe it. But what's happening is a package is being dropped. If it's the package is on the helicopter that's ascending, well, then so is the package. So we know that right away that our initial velocity is 7.50 meters per second. So we're going to write that down. We also know that we're probably going to say upwards is positive. So let's do that as well. Okay, so we know that we can say that's positive. Now, at a height of 120 meters above the Earth, a package is dropped. Okay, what else did it just give us? It gave us this displacement, okay? Now, here's a tricky one. Is the displacement positive or negative? Well, it's being dropped, so its starting point is above the ground and it's going down to the ground. So this is actually going down, so therefore the displacement is negative 120 meters. Okay, because it's starting below, or ending below where it started. So therefore that's a negative displacement. So this package is dropped at a height of 120 meters above the Earth. How much time does it take for the package to reach the ground? Okay, there's one other piece of information that we know that it didn't give us, and that is, of course, acceleration. Anytime something's dropping, we know it's acceleration, which is really nice. Okay, so there we go. We know the acceleration, and we're looking for time. Okay, so this doesn't have the situation of going up and back down to the same height. It's going even further down from that, so we can't really use that stuff. So this is the information we have. And again, I want to always look for equations that have the stuff that we have that we can use. So the thing is, if you look at every single other equation that has to do with acceleration and time and velocity, all the time ones have final velocity in it as well, other than this one. I think it's plus or minus. I can't remember at the moment. Let me tell you why this isn't going to work. We're trying to solve for time. Okay? Sorry, this is VI as well. Now, this is a really nice one to use when the initial velocity is 0. Is the initial velocity 0? It absolutely isn't. And so then you have a number here and a number here and a t there and a t there, and you're trying to solve for t, and you can't. Okay? If you've taken Math 20, then by the way, you can use the quadratic formula if you really want to, but honestly, why go for it? Because there is a better way to do it. So what's going to happen is, I don't think I can go right to finding time, because every other equation that I could use has the VF, okay? But here's what I can do. There's this other equation. It doesn't have time as part of it, which is what I'm looking for, but it looks like this, right? We used this in the last one. So why would I want to use this first? Well, the reason is because if I find final velocity, then I can find time much easier. So that's actually what I'm going to do, because my other three acceleration equations, other than the one that I just talked about, they have time in them, but they also have final velocity, which I just don't have. But I can find it, so that's what we're going to do here. Okay, so my final velocity is equal to the square root of VI squared plus 2AD. One really important thing I want to point out, though, when you take a square root of something, it's plus or minus. Okay, don't forget about that minus. That's going to be really important, because when you take a square root, it's never going to give you a negative number in your calculator. So this is a situation in which you have to think for a second and go, oh, is my final velocity positive or negative? So let's plug in the numbers first. Don't forget to square that. It's a common mistake. Still remember your negatives here. Okay, acceleration is negative, displacement is negative. Okay, so what we get is we get a value of 49.1 meters per second. I have a question though. Is this positive or negative velocity? Okay, think about it. It's kind of dropping, it's starting there, and then it's going way down to the ground. So my initial velocity is upwards. What's my final velocity? Downwards. So therefore, my final velocity should be negative. And that's only the reason because if you take the square root of something, the answer could be positive or negative, right? Take the square root of 25, the answer, so much of the time we just say the answer is 5. But the answer could also be negative 5, because guess what? Negative 5 times negative 5 is positive 25. Okay, so now we have our final velocity, and we're going to use this guy to find the time, okay? So there's two main equations that I could use to find the time. Don't use either of the ones where they have time in two places, though. It just doesn't work, okay? So I'm just going to start this on a new slide, though, just because, yeah, it's going to make our life a little bit easier. So what equation am I going to use to find the time? Well, I can use this one, or I can use the D is equal to, I don't know, VF plus VI over 2 times T. I think that's what it is. You can also use that one. This one is easier to rearrange for time, though. So I'm like, well, might as well just use that one, because technically, you know, you multiply both sides by T, divide both sides by A. But what kind of ends up happening is the T and the A just end up switching spots, and it makes our life so much easier. Yay! So, again, what was my final velocity? Do not forget the negative. You guys, the negatives and positives are the difference between correct and incorrect answers. Oh, I just put a squared there. There's no squared there. Let's get rid of that because that just looks messy. Okay, and then I'm going to subtract 7.5 meters per second. That's its initial velocity. And we divide that by negative 9.81 meters per second squared. Okay, and if you're freaking out and going, we can't have negative time, guess what? Look, if you put the negatives in the right place, you get positive time, because, yeah, you should never have negative time. If you got negative time, you did something wrong. We get positive 5.77 seconds. Our question did give us 3 significant digits, so that's what we want in the answer as well. Okay, so that's that question. Let's move on to the next one. We have a stone being thrown vertically upward with a speed of 12 meters per second. Okay, what did it just give us? It gave us initial velocity, so let's make sure we pay attention to that stuff. Okay, I'm going to write it up here because this one gets a little bit crazy. So my initial velocity is 12.0 meters per second. Okay, what else? It gave us the edge of a cliff is 75 meters high. So it's thrown vertically upward with a speed of 12 meters per second from the edge of a cliff 75 meters high. What's the point of having it the edge of a cliff? Well, think about it. You throw it up and it comes back down, and if you just threw it just a teensy bit horizontal, guess where it's going? It's going down the cliff. Okay, so we actually have a situation like this happening, where this is 75 meters, and the ball is then going to be going up like this, and it's going to be coming back down like that. So it's going to be ending lower than where it started. So that's kind of important to know. Okay, what else do we know? We know acceleration. Didn't give us acceleration, but we always know if something's falling, there's the acceleration. It did give us displacement. Again, have to think, is it below or above its starting point? Because we're obviously going to be saying that upwards is positive as we do in these situations. So its displacement is below where it started. So the displacement is negative 75.0 meters. Now, a lot of you are going to be going, but what? It goes up and then it goes down. So what about that? Well, that's not part of its displacement, is it? It's part of its distance, but it's not part of its displacement. Okay, so how much later does it reach the bottom of the cliff? Then we want to know its speed just before hitting. And then we want to know the total distance it travels. So we are going to need to figure out how much it goes up and down. Okay? Now, if you think back on the question before this one, remember in that one how we were trying to find time? This was all the information we had. And we had to find final velocity first. Oh, so this is messing you up where you actually have to do B before A. And that's okay. It happens. So sometimes you have to ask yourself, look at your data, look at the 5 acceleration equations and say, instead of what is the thing trying to get me to find, what can I find? And again, if we look at this equation, we can say, oh, I can find final velocity pretty easily, right? It shouldn't be difficult because I just square root both sides. I can get final velocity. I have initial, I have acceleration, I have distance. So sometimes that's what you want to ask yourself instead of going, how the heck do I find time? How the heck do I find this? How the heck do I find that? Just say, what can I find with the stuff that I have and the equations that I have? Okay, so I'm still going to put that plus or minus in there just to remind you. Our initial velocity is positive 12 meters per second, right? Because it's going upwards. Plus 2 times our acceleration, negative 9.81 meters per second squared, times our displacement, negative 75 meters. Okay, and again, is my final velocity positive or negative? Well, final velocity is right there. It's heading down towards the ground, so it's got to be negative. So remember, your calculator is not going to tell you that. This is where you have to be smarter than your calculator. Okay, what do we get? We get negative 40.2 meters per second. So there's my final velocity. So that's actually the answer to B, not A, which is fine. You don't necessarily need to go in the order of that it's telling you, but now we can go back and do A, just like we did in the previous example, okay? So again, finding time, once we have the final velocity, it's nice and easy with this equation. Okay, I just switch around the time and the acceleration. And there we go. So we should just be able to go final velocity, which again was negative 40.2 meters per second. So this is where if you didn't get that negative there in there, this is going to totally mess you up, right? Because then we got to subtract 12. And 40.2 minus 12 is a very different question than negative 40.2 minus 12. We divide that by our acceleration. And what do we get? We get a time of 5.32 seconds. Notice how all my answers have 3 significant digits, just like, oh, look at that, 3 and 3 there. Interesting. Okay. So there's my answer to part A because it asked for the time. So we did B first and now we're doing A and now we got to do C. Okay, so I want the total distance it traveled. So again, what do we have going on here? We have this 75-meter cliff. It's going up, it's going down. So we obviously know from here to here is 75, right? So what do I need to know? I need to know here to here, and then therefore there to there. I need to know how much distance that is. So what's special about this? Well, that's at its highest point, isn't it? It's at its maximum displacement. So can I find the distance to that top first? What do we know about this point right up here that's really special? If it's not coming to you, it's that the velocity here is 0. Okay, I'm calling it my final velocity just for now. Okay, that's a special thing we know about that point. is that at the very top, it's 0. So if I know that, I think I can probably find the distance it takes just to go from the top of the cliff to its very highest point, right? So if I look at, say, this equation, which, by the way, I don't want to look at an equation with time in it because I don't know how much time it takes to get to the top, do I? This time is for the whole thing. I want to know how much time it takes just to get to the top. Well, I don't even need to know the time, because if I look at this equation, now in this equation, my final velocity is 0, right? Because I'm specifically choosing to the top there. So my final velocity is 0. I know my initial velocity is still 12. My acceleration is still negative 9.81. Oh, so that makes finding that distance so much easier, doesn't it? So that's what we're going to do. So we're going to go ahead and find distance. We know it's negative VI squared over 2A. So let's find that, okay? So again, when we find that, and remember, this is just the distance to the top, we should get 7.34 meters. Okay, awesome. So what does that tell us? That tells us that we know this distance right here, that's 7.34 meters, right? And then guess what? This distance is exactly the same. So that's also 7.34 meters. And then the distance from there to the bottom is 75 meters. So we can absolutely find our distance without any problem whatsoever. So our total distance is really that 2 times that 7.34. Okay, because it's going up and it's going down, plus that 75 meters that the cliff that it's going down to the bottom of the cliff. So my total distance is 89.7 meters. Okay, so yeah, I'm throwing lots at you here. So it's really important that you just understand the circumstances of what's going on, because there's all this background information that is so prevalent and so important that you know while you're doing these kind of questions, because the question's not going to give that to you. It's not going to say, remember, at the top of its motion, it has a velocity of 0. Remember, this displacement is negative. Remember, the final velocity is negative. It's not going to tell you any of that stuff. So you need to know that about this kind of situation, and that's what makes it so difficult, right? Because there's so much background information just behind already the fair amount of words they give you. Okay, so look at that situation again, do a bunch of these questions so you know what's happening at each point in the motion. Okay.